This is a book summary of linear algebra done right, a rigorous undergraduate linear algebra textbook from the Undergraduate Texts in Mathematics series. It emphasizes abstract vector spaces and linear maps with determinant-free proofs and covers inner product spaces, operators, eigenvalues, and multilinear algebra. Written by Sheldon Axler. The book is 390 pages long and was released in 2024 by Springer Nature Switzerland AG. Chapter 1 introduces the basic language of linear algebra by defining vector spaces and developing their elementary properties. It begins with complex numbers C, showing how they extend real arithmetic, including I2 equals, and presenting C as a field with familiar addition, multiplication, inverses, and distributivity, while using the symbol F to denote either R or C, so results apply to both real and complex settings. The text then generalizes familiar 2- and 3-dimensional spaces to Fn and Cn, and to spaces of sequences or functions like f infinity and fs, explaining that a vector space consists of a set with an addition and a scalar multiplication satisfying commutativity, associativity, and additive identity and inverse, a multiplicative identity, and distributive laws. Substantial emphasis is placed on the interpretation of vectors as elements that can be added and scaled, with geometric intuition drawn from R2 while acknowledging that high dimensions are handled algebraically. The section on subspaces shows that a subset is a subspace if it contains the zero vector and is closed under addition and scalar multiplication, and it introduces the sum of subspaces, which is the smallest subspace containing given subspaces, as well as the notion of a direct sum, where every element has a unique representation and the intersection of summands is 0. Numerous examples illustrate subspaces, e.g., subspaces of R2 and R3, spaces of continuous or differentiable functions, and sequences with limit 0, and how sums and direct sums behave in practice, including UW and criteria for when a sum is direct. The chapter also covers additional tools, such as the complexification VC of a real vector space, defined as V times V with complex addition and multiplication, linking V to a complex vector space. Chapter 2 develops the theory of finite-dimensional vector spaces by introducing spans, linear combinations, and the distinctions between linear independence and dependence, culminating in the notions of bases and dimension. It begins with the basic notions: a linear combination AV plus AMVM, the span of a list, and the fact that span V1. Vm is the smallest subspace containing those vectors. It then defines linear independence and the linear dependence lemma, which says a dependent list contains a vector in the span of the preceding ones. Key examples show when a vector lies in a span, when a list spans a space, and that spans 0. A section on bases 2b introduces a basis as a list that is both linearly independent and spanning, with the criterion that every vector in V can be written uniquely as A1V1 plus ANVN. Examples include the standard basis of Fn and bases for subspaces of F3, and the fact that any spanning list contains a basis while any independent list can be extended to a basis. 2. 32. The dimension concept, 2c, is defined as the length of any basis. Two bases of a finite-dimensional space have the same length, so dim V is well defined, and dim U less or equal to dim V for subspaces, with linear independence of the right length guaranteeing a basis. 2. 39. The chapter also presents a formula for the dimension of the sum of subspaces. Dim V1 plus V2 equals dim V1 plus dim V2 minus dim V1 V2, and discusses direct sums, finite-dimensional subspaces, and analogous set theoretic ideas. Throughout, standard bases such as 10, 0, and PM, F spaces 1, Z. ZM illustrate these concepts, and the text notes the existence of bases in every finite-dimensional space and the extension of independent lists to bases. The chapter ends with leading results on dimension and sums, and even closes with a literary quote from Frankenstein to illustrate conceptual breadth. The text introduces linear maps as the central objects of study, defining, denoting, and illustrating them with concrete examples: zero map, identity, differentiation on polynomials, integration, multiplication by x2, backward shift, and general maps between finite-dimensional spaces, and establishing their basic algebraic structure. It defines L, V, W as the set of all linear maps with pointwise addition and scalar multiplication, and shows that composition acts as multiplication with associativity, identity, and distributive laws, while noting that ST generally need not equal T as a key result. The linear map lemma shows that a linear map is uniquely determined by its values on a basis, and the matrix perspective is developed. the matrix MT records T's action relative to chosen bases, so that MST equals MSMT. The matrix of a map, column-row interpretation, and change of basis formulas tie linear maps to matrices. The section then introduces null spaces, kernels and ranges images, injectivity and surjectivity, and the fundamental rank, nullity theorem dim v equals dim cur t plus dim im t for finite dimensions, with consequences that maps from higher to lower dimension cannot be injective and maps from lower to higher dimension cannot be surjective. It also covers invertibility and isomorphisms. A map is invertible if it is both injective and surjective. The inverse is unique. In finite dimensions, invertibility of T corresponds to invertibility of the matrix MT, and LV, W, Fm times N, via M. The text then extends to duality. Linear functionals, the dual space V, dual maps T, annihilators, and the transpose relationship MT letter 1D40, along with the notions of quotient and product spaces, their dimensions, and how duals and biduals interact. Together, these ideas establish a cohesive framework linking linear maps, their matrix representations, rank nullity, duality, and quotients. The excerpt introduces polynomials by first revisiting the complex numbers. A complex number z equals a plus bi has real part re z equals and imaginary part im z equals b, its complex conjugates equals a minus bi, and its absolute value z equals sqrt, a 2 plus b2. These notions allow identifying C with R2 and interpreting Z as the distance from the origin, with key identities such as Z plus equals 2 re Z, Z equals Z2, WZ equals WZ, and the triangle inequality W plus Z less or equal to W plus Z. Zeros of polynomials are defined as roots P, lambda equals 0, and a foundational result shows that if P has a 0 lambda, then P, Z equals Z minus lambda, QZ for some Q of degree 1 less, which implies a polynomial of degree m has at most m zeros and guarantees the degree is well defined. The zero polynomial is given degree minus infinity for consistency. The division algorithm for polynomials ensures that for any p and s not equal to there exist unique q and r with p equals sq plus r and deg s, the fundamental theorem of algebra is presented in two versions. Every non-constant polynomial with complex coefficients has a zero, and Roman 2 such a polynomial factors uniquely up to order, as p, z equals c, z minus lambda 1, z minus lambda. The discussion explains how real coefficient polynomials may have non-real zeros that occur in conjugate pairs, and how this yields real factorizations by pairing non-real zeros into quadratics x2 plus bx plus c with discriminant b2 minus 4c0. For quadratics, the discriminant criterion b2 greater or equal to 4c determines when real roots exist, and in general real polynomials factor into linear real factors and irreducible real quadratics. Text notes that proofs, and even computational methods, provide ways to approximate zeros, and the two versions of the theorem imply a corresponding factorization over R chapter 5, then pivots to operators on vector spaces, defining an operator and invariant subspace, a subspace mapped into itself by the operator, with examples such as the differentiation operator on polynomials preserving degree less or equal to 4 and listing invariant subspaces, 0, v, null t, and range t. It also previews the central result that every operator on a finite-dimensional complex vector space has an eigenvalue, leading to a basis in which the matrix of the operator has many zeros. This chapter develops the core theory of eigenvalues and eigenvectors by starting from invariant subspaces and the one-dimensional case. A subspace span, V, is invariant under T exactly when TV is a scalar multiple of V, i.e., V is an eigenvector with eigenvalue lambda. In finite dimensions, eigenvectors from distinct eigenvalues are automatically linearly independent, giving a path to decompose V into eigenspaces. Central results include: a finite-dimensional operator has at most dim V distinct eigenvalues. An eigenvalue lambda satisfies TV equals lambda if T minus lambda IV equals 0. The zeros of the minimal polynomial Pt are precisely the eigenvalues, and Pt equals 0 if and only if Q, T equals 0 for any polynomial Q that is a multiple of the minimal polynomial. The minimal polynomial exists for every operator on a finite-dimensional complex space and has degree at most dim V polynomials in operators. Pt preserve invariance. Null Pt and range Pt are invariant under T over the complex field. Every operator has an upper triangular representation in some basis, so the eigenvalues appear on the diagonal. Diagonalizability is equivalent to V being the direct sum of eigenpaces, Equivalently, the minimal polynomial splits into distinct linear factors. In particular, if T has dim-v distinct eigenvalues, T is diagonalizable. The chapter also treats commuting operators. Commuting operators share invariant eigenspaces, admit common eigenvectors, and if both are diagonalizable, they are simultaneously diagonalizable or at least simultaneously triangularizable. The Gershgorin disk theorem provides a spectral localization tool. Illustrative examples include a real 2 times 2 rotation with no real eigenvalues and a 3 times 3 complex example whose eigenvalues follow from the minimal polynomial. And the minimal polynomial framework is used to analyze diagonalizability and spectral properties, especially for polynomials in T and for sums or products of commuting operators. Chapter 6 develops the theory of inner products and norms in real and complex spaces, starting from the dot product and its axioms, positivity, definiteness, additivity, homogeneity in the first slot, and conjugate symmetry, and showing how an inner product induces a norm via V equals SQRT, VV. It establishes core results such as the Cauchy-Schwarz inequality, the triangle inequality, and the parallelogram law, from which orthogonality and projections follow. Key theme is orthogonal decomposition. Any vector can be written as a sum of a component in a subspace and a component orthogonal to it, yielding the orthogonal projection poo and a distance minimization property. Poo is the closest point in the subspace to a given vector. The Graham-Schmidt procedure constructs orthonormal bases, enabling Parsifal's identity and simplifying coefficients, leading to Bessel's inequality. The Riesz representation theorem identifies finite-dimensional spaces with their duals, so every linear functional is inner product with a unique vector. The text also develops orthogonal complements, direct sums V equals UU, dimension formulas, and minimization results for distances to subspaces, plus the more, Penrose pseudo-inverse T and its use in best approximation problems. Chapter 7 then introduces adjoints, self-adjoint, and normal operators, their matrices, and eigenvalue properties, including that eigenvalues of self-adjoint operators are real. Chapter 7 develops the operator theory on finite-dimensional inner product spaces, emphasizing the structure and decomposition of self-adjoint, normal, and unitary operators, and linking algebraic properties to geometric ones. It first establishes key distinctions between real and complex spaces. For example, the 90 degrees rotation in R2 is a non-zero operator with orthogonal vectors to V, illustrating real space caveats, while in the complex setting TV, V determines T via T equals 0. And it shows that self-adjoint operators have real inner products, and in the complex case, diagonalizable with an orthonormal eigenbasis. The text develops the spectral theory. Normal operators on complex spaces are unitarily diagonalizable, with eigenvectors orthogonal for distinct eigenvalues, and self-adjoint operators on real spaces have the real spectral theorem. It also notes a real, complex dichotomy via the decomposition T equals A plus IB with A B self-adjoint and commuting. It then covers practical factorization tools, including the QR factorization and Kolsky for positive definite matrices, the polar decomposition T equals S square root T asterisk T, with S unitary, and the broader framework of the singular value decomposition, SVD. For any T, there exist orthonormal bases E1, M in V, and F1. Fm and W such that TV equals some SKV, EK leading to T equals BDC, and to rich consequences such as the equality T equal to the largest singular value, the relationship between eigenvalues and singular values, and the interpretation of T and adjoints via SVD. The SVD also yields geometric insights, including volume changes by the product of singular values and optimal low-rank approximations. The chapter culminates in a suite of consequences and applications, including the polar decomposition, unitary isometry theory, and the interplay between spectral and singular values, with several illustrative examples, such as a real 2 times 2 rotation and a normal but not self-adjoint matrix, and computational procedures that connect theory to matrix factorization and numerical methods. Chapter 8 develops a structural framework for operators on finite-dimensional complex vector spaces by studying powers and null spaces, generalized eigenvectors and generalized eigenspaces, and the resulting Jordan form. It starts from the monotone increasing sequence of null spaces null tk, proves that these sequences stabilize, and that null t dim v range t dim v equals v, and uses this to motivate generalized eigenvectors. Non-zero v with t minus lambda I, kv equals 0 for some k, which leads to the notion of generalized eigenspaces g, lambda t, and the fact that g, lambda t equals null, t minus lambda I dim v. On a complex space, there is a basis of V consisting entirely of generalized eigenvectors, and V decomposes as a direct sum of the generalized eigenspaces for the distinct eigenvalues lambda, with T restricted to each G, lambda. T equal to lambda I plus a nilpotent part. Consequently, eigenvectors corresponding to distinct eigenvalues are linearly independent. Every generalized eigenvector corresponds to a unique eigenvalue, and the multiplicity of an eigenvalue lambda is dim G, lambda T, summing to dim V. This framework yields the Jordan form. There exists a basis in which T has a block diagonal matrix with Jordan blocks, each block having the eigenvalue on the diagonal and ones on the superdiagonal. Nilpotent operators have Jordan bases with all diagonal entries 0, and 8.46 confirms that every operator on a complex space has a Jordan basis. The theory also encompasses the characteristic and minimal polynomials, Cayley, Hamilton's theorem, and the trace. The characteristic polynomial has degree dim V, and its zeros are the eigenvalues with their multiplicities. TRT equals the sum of eigenvalues counted with multiplicity and TR, sint TRTS. The chapter provides concrete examples, including a T on C3 with eigenvalues 0 and 5 and its generalized eigenvectors, and introduces the notion of block diagonal matrices and their relation to generalized eigenspace decomposition, culminating in a cohesive, basis-free understanding of how operators decompose into simpler, well-structured components via Jordan theory. Chapter 9 develops the foundation of multilinear algebra and determinants by first treating bilinear forms on a real vector space V. It defines the space V, 2 of all bilinear forms, introduces the matrix of a bilinear form with respect to a basis, and shows how composing a form with an operator T yields new forms with matrices M, alpha equals M beta MT, and M rho equals M, T letter 1D40 M beta. It then presents the change of basis formula, A equals C letter 1D40 BC for the matrices of forms and gives examples, including beta, P, Q equals P2Q3. The text then studies symmetric bilinear forms, showing their equivalence to symmetric matrices in all bases, or some basis, and proving diagonalizability, in particular via an orthonormal basis in real inner product spaces, spectral theorem. It defines alternating bilinear forms, proves that alpha, VW equals minus alpha, WV, and shows that the space V, dim V, alt has dimension 1. It also proves that every bilinear form decomposes into a symmetric and an alternating part, and that every quadratic form Q on V arises from a unique symmetric bilinear form, ρ with Q equals Q rho, with diagonalization of quadratic forms into a sum of weighted squares. The determinant is then introduced via the one-dimensional space V, dim V alt. Det T is the scalar by which alpha is multiplied under T, giving det T, which is multiplicative, invariant under similarity, and connected to eigenvalues product of eigenvalues over C. The text also derives Hadamard's inequality and the Vandermonde determinant formula and discusses properties of determinants under transpose, dual, and adjoint. Finally, the tensor product VW is defined as the bilinear functionals on V times W, with the canonical tensor VW defined by VW. Phi psi equals phi, V psi W, establishing dim VW equals dim V, dim W, and proving the universal property. Every bilinear map gamma V times W right arrow U corresponds to a unique linear map VW right arrow U, and conversely. It extends these ideas to M-fold tensor products, defines M-linear functionals and maps, and shows that dim V1 VM equals dim V1, dim VM, with orthonormal bases in tensor products arising from orthonormal bases of the factors.